Okay, so if we go back to the basic fundamentals of acids and bases, we define a strong acid or a strong base as something that completely dissociates in water. So a strong acid completely dissociates to give 100% H plus, 100% of the conjugate base. The weak acids and weak bases are involved in what? They only partially dissociates, which means what kind of reaction are we talking about? An equilibrium reaction. So if we think about the, let's see if this will work today. So if we think about an acid and a base with HA dissociating into H plus and A minus. That's a weak acid. If we think about a base, the way we look at a base, our base really. We kind of think of a base equilibrium as looking at something like this, where the base reacts with water. But again, it's an equilibrium. And remember, the relationship is conjugate base, and then this is the conjugate acid of that base. And for the acid, if we had H plus, or if we have HA, and that reacts with water then to form H3O plus and an A minus, that this is our acid and that's our conjugate base of that acid. So both of these are weak. These are weak systems because they're partially dissociating. So what I would say then is I would say that the conjugate base of a weak acid, which would be A minus and HA, since it's still involved in an equilibrium, since it's only partially reacting, the conjugate of weak is weak. Okay, the conjugate acid or conjugate base of a weak acid or base is still weak because we have this equilibrium going on in both directions. When we talk about strong, and this is a new way of looking at things, because I don't know that all the general chemistry instructors think of this or present it this way. But let's take HCl. We're all in agreement that HCl is a strong acid. It's one of the ones that you know completely dissociate, which is actually it's not a lie, but it's an oversimplification because it doesn't 100% dissociate. But we'll leave that aside. We're going to form H3O plus and Cl minus. Okay, so there's that equilibrium, except why didn't it do that? Okay. Why did it just decide to erase it? I quit. There's supposed to be a plus Cl minus there. If this thing completely dissociates, my Cl minus that's on your paper but not mine, is Cl minus base? Does Cl minus react with water to form H3O plus? If I could go get some salt and I pour it in the water, is the pH going to change? No. It's not going to change from sodium, it's not going to change from the chloride. So in my terminology then, strong, because it's completely dissociated, leads to something that doesn't reverse, and so therefore this is a non-base. It's not a base. So chloride doesn't act as a base. Same thing would be true for bromide, iodide, any of those that we consider to be strong bases, or strong acids. Okay. Same thing would be true for a strong base. So the idea here is that we have to think a little bit about weak is weak, and the opposite of strong is not or non. Okay. So that's how we want to think about our acids and bases. So if we go back to the questions, this is something that we always have to clear up. And even not even necessarily clear up, this may be the first time you're kind of hearing about that. Just a note about the online quizzes. So sometimes I go back and I regrade them and I give credit because sometimes I'm asking these questions to see what your answers are. Okay, so like for this one, if I remember, we'll go back and actually give credit for either one of those two answers because I don't necessarily know that was in the video. So don't get all freaked out. I could hide the grade book from you so that you had no idea what score you got. And I think about that every time I get 5 emails after somebody takes the quiz and the same thing happens in lab too. The lab ones I have to grade all of them. So I do that afterwards, but every time I get an email like, I think I got everything right and it was marked wrong. Those are the little more harsh ones. Then I've calmed down. But actually, I like that. I like that because that usually stirs the discussion. Why did I get that one wrong? So you'll see the grade. You shouldn't see the answers, but you should see the score in a grade book. So that's fine. And like I said, I go back. These are small points, but they're also the point of discussion. Okay. So does that make sense to everybody? Weak, opposite is weak. The opposite of strong is non. It's not a base or not an acid. Okay. And we're going to be talking more about acid-base chemistry because the problem is all the acid-base chemistry that you learned in general chemistry was all in what solvent? Water. Guess what we don't use in organic? Water. We use organic solvents. And so if we really wanted to talk about pHs, they don't really exist. So we have to talk about pKa's, and we have to completely adjust our frame of reference. Not today. So this is kind of an entree into that. Okay. Is there anything else on the quiz that most everything else was good? And this is what I see when I look at it. This is the kind of view I'm looking at. There's some other educational statistics in there that I won't bother you with right at the moment. So this is our starting point. What else? What else do you have about the lecture video, etc.? I heard curved arrows. We can come back. We can talk about curved arrows. I will.
And how you do the line, you have to draw with the structure afterwards, do like CH3 or C that.
Like I sort of did the other day. Okay, we can do that. What else was a question? Did everybody try that problem I left you with on Friday, the CH2 with the 2 N's? So it was That one. And there were 3 of them, if I remember. Oh, and there was one big mistake, right? This all has a negative charge. So these are all anions. That makes a big difference in the structure. So there were 3 of these for CH2, N2 minus. Does anybody want to volunteer a structure that you got? Okay. What do you want to do with, how many lone pairs on this carbon? Bond to the nitrogen? Okay, double bond. Any lone pairs on this nitrogen? On the N nitrogen. Not on the middle, or not on the middle nitrogen. Any formal charges? Okay. There's one resonance structure. Does that look good? Anybody have another one? What?
Should the center nitrogen be plus 1?
Yeah. So maybe was this an anion or was it neutral? Well, this will happen more often than I want it to, where I get confused. All right, so the -1 had an issue, didn't it? Okay, this is a neutral molecule, sorry. All right, let's just start from scratch here. Here's a resonance structure for the neutral CH2 N2. Is there another one that I can draw? Like that? A lone pair on the C. Okay, if that was a negative, right?
No, and then there's going to be another lone pair.
There's a lone pair on the N. Any more lone pairs? You know what? Let's forget about that lone pair. So let's just do it as a neutral. Let's do it as a neutral molecule. What?
Yeah, there's still a lone pair on the C.
Actually, no, there isn't. I'll show you why in a moment. Now, we're confused. Let's totally forget about the negative charge and let's just do this as neutral. So is that a resonance structure of our neutral CH2 N2? Is this a resonance structure? How about formal charges? For this structure, forget about what you've written. For that structure, are there formal charges? Where? Where do we want a formal charge?
A positive one on the middle end, and then negative one on the C.
Oh, sorry, yeah. Forget about that one. Okay. So that's a second resonance structure for the neutral CH2N2. Right? At the last end, the N on the end has a 0 formal charge in that structure. So there's a second resonance structure. Now, why is there no... Wait. Now I'm confused. Oh, no, I'm sorry. I'm confused. Sorry, you're right. You were right all along. There we go. And you have to decide, am I just playing along or am I really confused? And now I've confused everybody. Something didn't add up there. How can I have a negative charge on a carbon with no lone pair? Right. Now, let me work in the idea of the curved arrows here. We're all in agreement that the structure on the left is okay as a neutral molecule? How did I get what? How do I get the structure on the right from the structure on the left? Let me do this. How about I take this pair of electrons and I use it to form a triple bond? Okay. And without the circle, if I just use that curved arrow, that would show that I'm moving that pair of electrons from the nitrogen to form a triple bond. Okay, and a curved arrow with a full-blown head here indicates the movement of 2 electrons. So I'm going to take this pair of electrons, that 2 electrons, and I'm going to move it to form a triple bond. That's going to leave the nitrogen with one lone pair, and now I formed a triple bond. Are we all in agreement that that's the first step to forming the triple bond? But can I stop there? No, because if I stop there, what happened? The middle nitrogen has
somebody has 5 bonds. The nitrogen.
This nitrogen would have 5 bonds. The middle nitrogen would have 5 bonds. So I have to do something else. I have to take this pair of electrons in this double bond and give it to the carbon. So I have to break the CN double bond and give that lone pair to the carbon. And then I've now got a nitrogen-nitrogen triple bond, a carbon-nitrogen single bond, but the lone pair is now on the carbon. Are we all okay with that? So the curved arrows can either go from a double or a triple bond. They never go from a single bond right now. And it shows how I could move that double or triple bonded pair of electrons and either give it to an atom or give it to the bond next to it. So if I wanted to make the right-hand structure out of the left-hand structure, I would need to move the arrows in that direction. This lone pair to form the triple bond, this double bond, give it to the carbon to form the lone pair. And so that's how I get this resonance structure B from resonance structure A. Does that make sense? So then let me ask you a question. Can you now put the arrows that would turn B into A? So how would I convert B into A? Why don't you take a minute, draw the arrows. Better yet, why don't you draw the arrows on the chalkboard and then you can hold them up. So write the arrows that would go to make B into A. And to do that, you have to remember that something with a negative charge Well, we don't even need to deal with the negative charges, do we? Something with a negative charge means that it's got a lone pair. Anything that's negatively charged always has at least a lone pair. Okay. So how am I going to convert B into A? Okay, are we ready to hold up our hold up your pull out my phone and take a picture, and then I could go back and see who's right and who's wrong, but I'm not going to do that. That's your judgment. It looks like we got it, even though you were hesitant to think you could do that. All right, so what am I going to do? I'm going to take this lone pair on the carbon. I'm going to use it to form the double bond, but then at the same time, I need to break the nitrogen-nitrogen triple bond and give it to the nitrogen to work backwards. Okay. So what I'm trying to do here is to show you, trying to get at the curved arrows with these resonance structures, because that's actually how we can determine other resonance structures. If I find one good one, now I can start thinking about moving the pairs of electrons around, and the way I show that I move those is by using the curved arrow. Because a curved arrow tells you where the pair started out, and a double or a triple bond is nothing more than a pair of electrons, where it started out, and then the arrow tells you where it ends up.
I have a question. On like the sapling homework, sometimes you do like half an arrow.
Yeah, a half of an arrow, which looks like this, the fish hook, that indicates the movement of one electron. We're not to that point yet. So sapling has, I think, the ability to switch between a half arrow and a full arrow. So if it asks you to do that in chapter 1, you want to switch it to a full arrow. This is chapter 4. We'll start using half arrows. Same principle, though. Any arrow, it's from here to there. So it shows where the electrons are moving. And then after you do that, go back and refigure out the charges. Because I won't confuse the issue by the arrows mean the movement of electrons, not something else that I won't say. And then somebody will say, but you said that. No, I said no, that's not the case. So arrows show movement of electrons. And right now, full arrow pair. So if I can only come up with one resonance structure, I can actually generate others by moving pairs of electrons around, by moving the arrows. Okay. Now, problem is completely different than what I had suggested on Wednesday, because I said 3. Is there another possible one from these two? And the answer is no, not without violating the octet rule. So we can eliminate, if I can, we can eliminate the third. Okay, so there's our two resonance structures, A and B. So, what do you think I'm going to ask you to do next? What? Which one? Yeah, I might ask that. We could sketch out the hybrid. Sure, let's sketch out the hybrid. I actually had multiple questions that I was going to ask, but that was one of them. So let's sketch out the hybrid then. So why don't you sketch the hybrid out and then you can hold it up. Oh, this is going to be fun too. So write out the hybrid and then let's take a look at that. Okay, so all right, so what it looks like, two parts to the resonance hybrid, right? We need to average the bonds and then, or vice versa. So I need bonds and charges. So if I look at the bonds, I've got double, single, partial double. Double, triple, partial triple. I'm half done. Now we need to average the charges. So if I look at carbon, it's 0, minus 1, average. 0 charge, minus 1 charge, average charge, delta minus. Let's do the nitrogen on the end. Minus 1, 0, average, delta minus. Now the middle nitrogen. That's the one we got to watch out for. What's the average charge on the middle nitrogen? Plus 1, plus 1, plus 1. So we have to make sure that the nitrogen gets a full plus 1. Okay. And that's okay. Like I've been doing this a long time, and that's a common, when we first start, that's a common thing that people, you got to make sure if it's the same in all the resonance structures, it's a full-blown charge. So not all the charges are delta. So there's my resonance hybrid. Okay. All right, we okay with that? Excellent. So now my other question. What's left? We've drawn the resonance structures. We've drawn the hybrid. And so what's left? Paul? Which one's more stable, A or B? So that's the question. Which one is more stable, A or B? So you can go in, well, and I'll make C an option. C would be that they have the same energies. So which one is more stable, A or B? And you can click in your answer and we'll see what we got. Okay. All right, got an answer from everybody? I'm going to close it out. All right, I've got 77% A and 23% B. Is that correct? I mean, 77% of you would say yes, that A is the more stable. How am I making that decision? How am I deciding between A or B? Which one?
Completed octet, small formal charge and no formal charge, and the more electronegative one agrees with formal charge.
Okay, so they all have completed octets? Yes. Do they all have small formal charges? They each have a +1 and a -1, so they're tied. So we go to the tiebreaker. The difference is who gets the negative charge, carbon or nitrogen. We go to the periodic table. Which element is more electronegative? Nitrogen, so nitrogen should get the negative charge. And so, in this case, A is indeed more stable. Okay, so we always use those three rules. Completed octets, followed by small charges, numbers of charges, and then the electronegativity.
Do we draw resonance structures that don't have completed octets?
Yes. And I might even have one to get to it. Now, that's actually, yes, we will draw perfectly valid resonance structures that have incompleted octets. So then the question becomes, well, if I ask you to do this, like for next Wednesday, I have a take-home quiz for you, I'm going to say, write all the resonance structures where each atom has a completed octet. So for the moment, whenever I give you a problem, I'll tell you whether you're allowed to write completed octets or not. So for the moment, they have to have completed octets. And for the moment, we're not going to do expanded octets. So I'll tell you, but will we have a carbon with 3 bonds and a positive charge? Tons. We're going to have tons of those. And technically, those aren't stable by our rules, but they aren't stable, but we're still going to draw them. So we will get to that point. And then the question becomes, do you see any of those on sapling? And the answer is you might. You might see them on sapling. But for the problems I give you, I'll always say only completed octets. The carbon with 3 bonds and a positive charge is actually okay. It's not very stable, but it's something we draw. Okay, so the problem didn't work out exactly like I wanted it to, but we've got 2 resonance structures, and it looks like we're getting the hang of determining stabilities. Okay? All right, so we okay with that? And yes?
So we just don't pay attention to the lone pairs when we do the hybrid?
No. There are no, I have to be careful how I say this. For the time being, there are no lone pairs in resonance structures. There's just bonds and charges. Now, where do the charges come from? They come from how many lone pairs it has. So, yeah, we don't put a delta dot. Right? We don't put delta dots. Yeah. So that's how the lone pairs figure into this. They give us the charge. Okay. What else was in this? We got kind of the curved arrows a little bit. What was the other question? Oh, the line ones. So let's say that I gave you a structure like that. That is the P or para-dimethoxybenzene from lab. Right? You had all these names. I might as well just call them unknowns number 1, 2, 3. You had solvents like methanol and ethanol, but the names are, we'll get to the names, but this is para-dimethoxybenzene. This is the shorthand structure for this. So how would I expand this into showing the carbons and the hydrogens? Well, what I would do is I would add in carbons at every intersection and every end of the line. So that's our first step. And then we add in how many hydrogens? Enough to give us 4 bonds. So that means for each one of these carbons, there would be 1 hydrogen. Notice that the carbons here already have 1, 2, 3, 4 bonds, and so they get no more hydrogens. And the carbons on the end would get 3 hydrogens, like so. And so now all the carbons have 4 bonds. Now, this is where I could start to condense this structure down. In other words, I could say that this group is a CH3 group. So I could very easily say that if I wanted to draw this structure back out again, I could have the O's with then CH3s at the end. So this structure would be something we would that we'll work towards, but this is a sort of a combination of a line bond structure and sort of a condensed structure. And I always like to show the CH3s at the end of the line just so there's no confusion. So let's do this. Take that one and draw it out and expand it. Expand it with all the hydrogens explicitly first, and then condense it down to CH2s and CH3s.
Should we assume that there are 2 lone pairs on each of those atoms?
Yes. Yeah, all of the atoms that have lone pairs, I may or may not show them. So yes, they would have 2 lone pairs. Unless there's a charge, it has the lone pairs. I tend to only show the lone pairs when I'm going to do something with them. So yeah, that would be fine. So you can write that one out. You don't have to write it on the board if you don't want to. But how would you expand? How would you draw it? And then once you get all the hydrogens in explicitly, you make it as CH2s and CH3s. could either put them as a CH. Yes, they're also 4 bonds. So carbon would have well, then it would have a negative charge. So if it had a lone pair that had a negative charge, I'm going to show that explicitly. So if less charges are shown, we always assume it's got enough hydrogen to make 4 bonds. Okay. Let's work to that one. Okay, so does everybody have? Here, I'll do this real quick, and we'll see if I can do it. I should probably just jump right to the final answer, but I'd put my carbon, my hydrogen, 2 hydrogens off that carbon with 3 hydrogens there, another carbon with a hydrogen, carbon with 3 hydrogens here, and then the carbon with 3 hydrogens there. Okay, so if I'm condensing this down, I'm condensing it down to have a CH3 attached to a CH, attached to another CH3, attached to a CH, yes, then to a CH2 and a CH3, and then up here with the CH2 with the Cl. So this, the one in the upper right-hand corner, would be sort of a completely condensed structure. And you can have in-betweens because you can leave off the CHs. Now, the question is, if I have a typewriter, if I'm doing this with a typewriter, and who knows what a typewriter is, but if I'm doing this with only the keyboard and I'm not drawing, which is what sapling does, how can I super condense that structure down? All right, in order to super condense that, I'm going to sadly have to erase this guy. So here's how this would look. Starting at the left end, I would have 2 CH3s. And the way you represent that is by putting CH3s in a bracket with a 2. Attached to those 2 CH3s is the CH. Then attached to that CH is another CH. But what's attached to that CH? Well, they would probably do this. They would say there's a CH2, CH3 in brackets, and then the CH2Cl. So when you're looking, that's how I would do it if I wanted to type the entire structure out without having to draw it. What you have to remember, and so if we jump right to this and say, how do I work backwards from here up? What you have to remember is that the carbons are the connections here. You never have a carbon attached to a hydrogen with another carbon attached to that hydrogen. Hydrogens can only be attached to uno things. That's the end. So if I'm looking at this, I see carbon, carbon. This carbon has 2 carbons off of it. This carbon actually has 2 carbons off of it. One is this group, and the other is that group. So you can see all these different kinds of structures. And with sapling, it's just easier for them to type it out with that structure. But that's how you would see it. So anything that's in parentheses means that these 2 groups are attached to that carbon. And this group is attached to that carbon. But then again, that group is also attached to that carbon. So that's like the ultimate condensed structure. And again, historically, it's just easier to type that structure out than it is to draw it. And part of the reason we're using the sapling is because it's one of the few electronic homeworks that lets you draw stuff, and then it has the ability to figure out what if what you drew was correct. And that's a computer science problem. A pretty significant one, I think. Does that help with that? So when you see those structures, that's how you back interpret them up to the original one. And again, as we do more and more of these structures, particularly with naming that's going to come about here in a couple weeks, you'll get more and more comfortable in looking at that and being able to see it in your head, or at least being able to jot it out. Okay. Was there anything else? The only other thing that was in this was the idea of acids and bases and thinking about equilibrium. So let's say, for instance, that I said, and this is a general chemistry problem, let's say I react an acid and a base, or I say, in this case, let's put H2S and SO4 2 minus in an equilibrium. What are the only possible acid-base products of this reaction? H. That's the only two possible products. Now, I think I have some homework problems or some practice problems where I give you the product. But in this case, if this is an acid-base reaction, there's only one of these things that has an H to donate. So we don't have to worry about, does it go this way or does it go this way? So in this case, the only acid-base products would be to give an H plus to the SO4 2 minus, and that will leave the HS as a negative charge. And hopefully I drew this right so the charges add up on both sides, because I got -2 on the left, -2 on the right. I'm good. So then the question is, well, so which way does the equilibrium lie? Does the equilibrium lie to the left, or does it lie to the right? And so the way we have to think about answering that problem is, the first thing is I need to identify the acid for the right-hand reaction and the acid for the left-hand reaction. Okay? In other words, I'm going to say that that is the acid going from left to right, because it's the one that donated the proton, right? And so what accepted the proton? This. Now let's think about right to left. If I'm going from HSO4 minus to SO4 2 minus, this did what? That donated a proton to HS minus, so this one becomes the acid and that one becomes the base if I'm looking at the reaction from the right to the left. Does everybody kind of see that? And if you're like, oh, I don't want to deal with right to left, just right to right. Just write the products on the right, write the ones on the left, and then hopefully you'll begin to see that. So looking at the equilibrium left to right, I've got an acid and a base. Going from right to left, I got an acid and a base. So once I identify them, my work's done. Almost. Because now what do I need to figure out? I need to compare this acid to this acid. And one of those two is going to be stronger than the other. Now, in the PowerPoint notes, there's charts that rank the acids up and down. Do you have to memorize that chart? No. If you need that chart, I'll give it to you. You need to know how to use it? Yeah, that'd be helpful. So if I look at that chart, I can determine which of those two acids is stronger. So where does the equilibrium lie? Which way does it go? The equilibrium will lie to the weaker side. And I can do this with the bases, right? I could compare base to base. Where's the equilibrium going to lie? Towards the weaker side. Here's an analogy that I haven't thought through, so it may not work. It's not a tug of war, it's a push of war. The side that pushes the strongest is going to knock over the weaker side. It's a pretty good analogy. Okay? So that's how we handle those kinds of problems. We'll talk more about those, but that was in there. That was the last thing. So, all right, I have a take-home quiz. So you can come up and get that as you put your stuff up front. That is due on Wednesday. And I'll post an electronic copy if you lose this one. It's actually, I think, already online.